C asks if the derivative is greater than 0 for all values from -1 to 5. And by definition, since it's strictly increasing, we know that the f prime is bigger than 0, and that's just by definition. For D, it asks if the second derivative is equal to 0 for values of -1 to 5. Well, to do that, to analyze that, we're going to look at the graph here. So I plotted some points, and we can see that the points here are going to look like this. And what I'm going to do is I'm just going to analyze the slope between points. So if I calculate the slope here, the slope between -30 and -2 is going to be a rise of 28, a run of 1. So I've got a slope of 28. So in between -1 and 0, I have some slope value, and I'm just going to put that there as 28. And I can check the slope between from 0 to 3. It's got a rise of 12, run of 3. So I have a slope value of 4 here. So at some point somewhere in here, I have a slope value of 4. And from 3 to 5, rise of 8, run of 2. So I have a slope value of 4 here as well. So somewhere between 3 and 5, I have this slope value of 4. So for the second derivative to be equal to 0, the slope of the slope must be equal to 0. So that means that f prime, well, the derivative, I should just say the derivative, the slope of this f prime graph must be equal to 0. Now, the fact that this graph is twice differentiable means that the derivative is smooth and continuous. Now, although I didn't draw this graph as smooth and continuous, it could be, a smooth continuous graph. It could look like this and is strictly increasing. This is also smooth and continuous because it's twice differentiable. That means then that the graph could look something like this. It could just go straight across. Well, if it went straight across, that would indicate a slope of 0. But even if it didn't go straight across, let's say it did something like this. The fact that it goes through these 2 points, and this graph is smooth and continuous, there must be some point in between these 2 points here at y equals 4 where the slope is 0. There's a horizontal tangent. And it happens at least once, because I could have this as strictly increasing, so it's just going to stay above 0, but it could look like this as well. And then I'd have horizontal tangents at, this point here and this point here. So considering the simplest case, where it just looks like this, we're going to say that there must be some horizontal tangent occurring right about there. Now, how can we state this with a concise definition or with absolute certainty? Well, we can invoke the mean value theorem. So in this case, we can say that the average slope of the slope, or the average value, average slope of the f prime graph looks like this. It's going to be the rise of 0 over the run of, whatever that is. We'll call that the change in x. And we know that the average slope must be equal to 0. So because this is smooth and continuous, so f prime is smooth and continuous, we can invoke the mean value theorem. So by MVT, f double prime of c is equal to 0 in the interval between somewhere in the interval of -1 to 5. Okay, so this is an application of the mean value theorem because we know that the average slope is equal to 0. That means that there must be some instantaneous slope or second derivative that is equal to 0 between these 2 coordinates here. Okay, because the slope is 4 here, the slope is 4 here. If it goes straight across, we have a slope of 0, which means the second derivative is 0. even if it's curved like this, no matter how we draw it, if it's smooth and continuous between these 2 points, which it is because it says it's twice differentiable, we know that there must be some point in between these two values, and by extension we can say that be somewhere between -1 and +5, because we know that these 2 points could exist anywhere from -1 to +5.